Today I have set up an experiment to demonstrate Heisenberg's uncertainty principle right here on my desk. I have a green laser pointer securely taped down, firing a beam through a narrow slit. To make the slit adjustable, I have mounted two razor blades into these candles. The laser passes through the tiny gap and projects a green spot onto a paper screen on the wall. What do you think is going to happen to the spot on the screen as I narrow the slit? Well, at first you see exactly what you expect. The spot gets narrower and narrower because the side of the beam are simply being cut off by the razor blades. If you stop there, it makes complete sense. But if you keep going, something incredible happens. The spot actually starts to spread out. You're squeezing the gap closed, yet the spot on the wall is getting wider. To understand why this happens, we have to look at Heisenberg's uncertainty principle. The principle is mathematically written as delta x times delta p is greater than or equal to h on 4 pi. This formula is about the position and momentum of a particle. X is the position of light photons and p is their momentum. Delta x represents our uncertainty in position and delta p is our uncertainty in the momentum. When multiplied together, they must always be greater than or equal to a very small number known as Planck's constant or h on 4 pi. In our everyday life, we don't normally notice this because everyday objects are much bigger than Planck's constant. But as we narrow the slit between the razor blades, we are decreasing delta x for those photons. We were getting more and more precise about exactly where the photons were passing through. Eventually, you hit a limit where narrowing it any further is going to break this uncertainty relationship. To keep the loss of physics intact, the uncertainty in the photon's horizontal momentum, delta p, needs to go up. Before, the photons were going perfectly straight, but now they were veer off to the left or to the right to compensate. The more narrower you make the slit to decrease the position's uncertainty, the more momentum uncertainty has to go up, producing a much wider beam on the wall. It is highly non-intuitive, but it is the way the world works. Now, there is a slight controversial nuance to this. If you view light not as a particle, but purely as a wave, all the light is doing here is diffracting. Diffraction is when a wave passes through a narrow slit, bends at the corners, and radiates outwards in all directions, which also explains the spreading of the beam. So, is it diffracting waves or particles obeying quantum limits? Either way, it's an amazing piece of fundamental physics you can explore with just a laser pointer and a couple of razors.